Section 2.5 continued. We were talking about continuity in this section, and now we're going to look at a few more things to do with continuity. The first is the Intermediate Value Theorem. And the Intermediate Value Theorem basically says if you have a continuous function, so f is a continuous function on a closed interval from a to b, so we see in the picture here we're looking at the interval here from a to b, okay? And if y naught, or y sub 0, is any value between f of a and f of b, okay, so we see it's between f of a and f of b, then y0 equals f of c for some c in ab. So basically it's telling us that whatever we find for f of a and then f of b, if there's a y value between those two things, then there has to be a corresponding c value so that f of that value, f of c, is equal to this. And of course the stipulation is that this has to be a continuous function. So if it's not a continuous function, that theorem does not apply. Now, this intermediate value theorem, as a consequence, it gives us a way to find actually the roots, or if there are any roots, of a continuous function over an interval. Because if f of a and f of b have opposite signs, like one is negative and one is positive, then there must be a 0 somewhere on that interval. So there must be some place on that interval where f of c is equal to 0, because if one is negative and the other is positive, according to this theorem, there has to be some value here that will give us 0. All right, so how can we use the intermediate value theorem to show that a function has a root on an interval? Well, this one simply says, show that this function has a root between 1 and 2. So all we have to do in this case is evaluate f of 1 and then evaluate f of 2. So f of 1 would simply be 1 cubed minus 1 minus 1, which is negative 1. And f of 2 would be 2 cubed minus 2 minus 1, which is positive 5. Okay? And so since 0 is between negative 1 and 5, which is f of 1 and f of 2, that means there has to be a value c in the interval from 1 to 2 such that f of c is equal to 0. That's the intermediate value theorem, because 0 is between these two values. Okay, so the intermediate value theorem basically shows us that there has to be a 0 somewhere between 1 and 2. Now, it doesn't tell us what the 0 is, but it narrows it down. So if we actually wanted to find the 0, we could look at 1.5 and see if that's positive or negative, and then we could split that interval in half, and then we could do that again and again until we get closer and closer to the actual 0, which is actually how certain calculators and stuff would do something like this when it has it solving and finding zeros. It just basically keeps narrowing it down to smaller and smaller intervals till it finally gets it accurate to so many decimal places. All right, so here's another example of the intermediate value theorem. It says, use the intermediate value theorem to show that this equation has a solution. Okay, so the first thing I'm going to do is actually I'm going to rewrite this so that I can see, I want to find a value of c and see if I have a value of c where f of c is equal to 0. Okay, so f of c, or f of x in this case, I'm going to actually just move everything to one side of the equation. So I'm going to call this the square root of 2x plus 5 minus 4 plus x squared. Okay, because I'm actually looking for also where 2x plus 5 minus 4 plus x squared is equal to 0. So that's what it means for this equation to have a solution, right? And so basically I'm going to call f of x the left-hand side of this thing, and I'm going to look at a couple values. I'm going to pick something nice like f of 0, because that's easy to calculate. And f of 0 here is going to be the square root of 5 minus 4, and then 0 squared is also going to be 0. So this is actually a negative number, because the square root of 5 is slightly more than 2. Okay, so it's a negative number. If I look at f of 1, if it turns out that f of 1 is positive, then I'm good. If not, then I have to try another value. So if I look at f of 1, I'm going to get the square root of 2 times 1, so I'm going to get the square root of 7. And then this is going to be minus 4, and then plus 1 is going to be minus 3. Okay, and so again, I actually have a negative number, so I haven't done anything, because again, the square root of 7 is slightly less than 3, because the square root of 9 is equal to 3. Okay, so this is still a negative number. So we'll go one more. Let's try f of 2. So f of 2, that's going to give me 4 plus 5 is 9, so the square root of 9, which is actually 3, minus 4 plus 2 squared is 4. Okay, so this is actually just equal to 3, which is now positive. Okay, and so since I have that f of 1 is negative and f of 2 is positive, that means that somewhere there's a value c somewhere between 1 and 2, such that f of c is equal to 0. Okay, that's by the intermediate value theorem. And this means that our original equation has a solution. Okay, so this original equation up here has a solution because we just found a place where f of c has to equal 0. All right, so there are actually two types of discontinuity. If you remember some of the graphs we looked at in part 1 of this section, the video for part 1, is that sometimes we just had a discontinuity because there was a hole in the graph, and sometimes we had a discontinuity because there was a jump or there was an asymptote or something of that form. So when we have a function that has a hole in the graph, so for example, this function here, sine x over x, is discontinuous at 0, okay? And the reason it's discontinuous at 0 is, of course, because we're going to have a denominator of 0, okay? So the function is not defined at x equals 0. All right, so since it has a discontinuity at 0, but we already showed that this limit actually exists. Okay, so in a previous section, we showed that this limit is actually equal to 1. All right? And so what we can do is we can redefine the function piecewise by saying at the point where it's not defined, or at the point where it is defined, we're going to just leave it as the sine of x over x. And then at the point where it's not defined, we're going to redefine it to be equal to the limit. So that means that when we take the limit of this new function f of x, as x approaches 1, we're going to get 1, and that's also going to equal the value of the function. And now we've redefined this function so that it is continuous everywhere. So when you can redefine the function by setting it equal to the limit at a point, then that is called a removable discontinuity. Okay, so we can remove the discontinuity by assigning the value of the limit to the function. All right, So basically what we have here is near 1, the original function, the sine of x over x, okay, that has a hole in the graph right here at x equals 1. And so all we did was we plugged up that hole by redefining it to equal, for the y value to be 1 when x is equal to 0. Okay, and so that is giving us a now continuous function. It's called the continuous extension of the original function. Okay, so this one says find any continuous extensions of the function x squared plus x minus 6 over x squared minus 4. All right, so what we're going to do is the points in question are the points that make the denominator equal to 0, which will be 2 and negative 2. Okay, so those are the values that are going to make this equal to 0. So those are the points where we're going to have some kind of a discontinuity because the function is not defined at those points. So we don't know yet whether these discontinuities are removable or not, but we can check them by looking to see if the limit exists. So if I look at the limit as x approaches 2 of my function, and then I also look at the limit as x approaches negative 2 of this function, if either of these limits exist, then at that point we'll have a removable discontinuity. So we'll go ahead and calculate these limits. So this is going to equal the limit as x approaches 2 of x plus 3 times x minus 2 over x minus 2 times x plus 2. And so we can actually cancel those out and get that this is equal to the limit as x approaches 2 of x plus 3 over x plus 2, which is equal to 2 plus 3 over 2 plus 2, or 5 over 4. So since this limit exists, we have a removable discontinuity at x equal 2. All right, so now we can do the same thing here. So this is going to equal, of course, the cancellation will all be the same. So this will also equal the limit as x approaches negative 2 of x plus 3 over x plus 2. Okay, and that actually gives us 1 over 0, which is undefined. So therefore, this limit does not exist. Okay, so that means we have a removable discontinuity here at x equals 2, but we have a non-removable discontinuity at x equals negative 2. All right, so what is the continuous extension of the function? Well, we'll just redefine the function. We'll let, let's call it g of x is going to equal the original function when x is not equal to 2, and it's going to equal the limit of the function 5/4 when x equals 2. All right, and so that makes this function continuous at 2, but we cannot remove the discontinuity at negative 2 because it is a non-removable discontinuity. All right, so basically what we did here is, again, we had this hole in the graph at x equals 2, and we plugged it up with the value of the limit here of 5/4. All right, last example here. This is an example. It says, for what values of a and b is the function continuous everywhere? And so we had a similar function in the last video where we had each of the pieces of the function is continuous, because a constant function is continuous everywhere, so these two are continuous, and a polynomial function is continuous everywhere, so the middle piece is continuous. So the only points in question where there may be discontinuities is, again, when we stop following this piece of the function, right, and we start following this piece. And similarly, when we stop following this piece and start following this piece, okay? So in that case, we need the limit to equal the value of the function. All right, so if we look at the f of -1, okay, when x is equal to -1, we're following this piece of the function, so f of -1 will be -2, okay? And so, of course, the limit from numbers less than 1 is going to also be -2. But if we want to look at the numbers, the limit as we're bigger than 1, okay, so if we actually look at the limit as x approaches 1 from numbers bigger than 1, then we're on this piece of the function. Okay, so we're on the middle piece of the function. So we're looking at ax minus b, and we want this to equal -2, because we want it to equal the value of the function, which is also the limit of this function as x approaches from the left. And so as x approaches -1 from the left, from the right, this is going to approach -a minus b. And we need that to equal -2. All right, similarly, when we jump from this piece to this piece at x equals 1, we have that f of 1 is equal to 3, because when x is 1, we're following this piece of the graph. And that's also going to be the limit from the right, but we also need the limit as x approaches, as x approaches 1. From numbers smaller than 1, so from the left. And in that case, when we're numbers smaller than 1, we're again on the ax minus b part of the graph, and we need that limit to equal the value of the function, okay, because that is our definition of continuity. The limit exists, it equals the value of the function. And so when x is equal to 1, this just becomes a minus b is equal to 3. All right, so now we basically just have two equations and two unknowns. Okay, so I have -a minus b equals -2, and then I have a minus b is equal to 3. So if I simply add these two equations together, I'm going to get -b is equal to 1, or in other words, b is equal to -1. And then if b is equal to -1, then a is going to have to equal 2, right? Because basically we can plug it in here. A minus -1 is equal to 3. So that gives us that a is equal to 2. Okay? And so the answer to the question, for what values of a and b is this function going to be continuous, that would be when a is equal to 2 and when b is equal to -1. Okay, so that will make the function continuous because the limit of the function will actually equal the value of the function.